Hi, my name is George Cybenko. I want to thank you for coming to this talk or watching this talk at least. Um, this work is done together with Roger Hallman, who's a PhD student and also a civilian at the NIWC Naval Warfare Information Warfare Center in San Diego. So what we can do in this talk is really start a discussion, incentivize you to read our papers. So here's some publication information where there are more details. And my email and Roger's email are listed here as well. So I want you to contact us if you have any ideas or insights that would help. Maybe we can work together. So the basic ideas that I'm going to talk about here are that multi-agent systems can collectively learn to adapt faster than a single monolithic agent because you have more learners and you have some way to share that information, for example. Exploration and learning requires making suboptimal action choices. Those choices can lead to attrition, the failure or compromise of agents because they're not, you have to sample the whole action space. So you have a trade-off between you have multiple agents and you're exploring the action space, but as you're exploring the action space, the number of available agents is being attrited. And so the learning adaptation rate decreases at the same time that the performance is increasing because you've used multiple agents to do the learning. So how do you model and analyze these competing factors, these trade-offs? So that's what I'm going to try to explain. So I'm going to motivate this. I'm going to say a few things, sort of tutorial on upper confidence bounds and corresponding sampling techniques, and then show you some results of some simulation to get a sense of what's possible. So why are we doing this? Well, there's a lot of talk these days about transitioning from small numbers of large, expensive, hard to replace systems, aircraft carriers, big server farms located in one place, things of that form, and replacing that with swarms of simpler intelligent systems. Okay, so things that are replaceable, less expensive, and so on. And in the context of military operations, which is the context in which most of my work is funded, this includes land-based, airborne, maritime, cyber, etc. So much of what I say isn't restricted to cyber solely. So attritable assets in general mean that you're going to trade cost and maintenance and reliability for reusability and expendability. So the trade-offs with attritable learning systems is that they could adapt faster, but then the adaptation leads to attrition, okay? Because I'm sampling actions and moves that are suboptimal to see what the whole action space is like. And so how do I trade those off? And the ultimate goal is to gain decision advantage where I can use these attritable assets in principled ways. I have minimal secure communications, coordinating things between multiple attritable assets. And then I am performing online learning during the engagement. So what I'm going to lead you through today is a way in which to model and in a principled way, attritable assets being used in online learning. And we're at a cyber conference workshop, so it's really, I'm going to set the stage with some cyber things. But in the end, what we'd like to have is a situation where I've got blue force, red force, defender, attacker that are in somehow a balanced situation. But then during an engagement, during an operation in an online way, the blue force can adapt faster and better than the red force or the attackers, and at some point during the engagement, end up dominating because of that ability to adapt faster and better. So the setup, I'm going to take a very simple example of an adaptive cyber defense situation. So I have multiple machines. Think of servers that are being attacked, and the attack signature suggests that multiple responses are appropriate. So how do I figure out which response? And I've listed a few here, like reboot, reconfigure, change some firewall rules, maybe quarantine, isolate a machine or an enclave. So I've got a variety of actions that I could do in the middle of a cyber engagement. And how do I adapt online and learn to use the best response quickly in a way that maximizes mission success probability? So I have to bear in mind that there is a mission. So this, I apologize for people who see this a lot, but the reinforcement learning setup is that I've got an agent operating in an environment. The agent can detect the state of the environment that's on the left. In that state, can perform an action, selects an action. Then the environment produces a new state and a reward or a punishment or some feedback on how good that performance was. Okay, so this is a basic reinforcement learning problem. And the question is, what's the best thing to do? Can I learn that by exploring the action space and the state space together? So very simple formulation of this is a multi-arm bandit formulation. And most of what I say is going to be applicable to a Markov decision problem more generally, but I'm just going to start with multi-arm bandit. So I have a, just like in that cyber defense scenario, I have multiple options in a multi-arm bandit formulation. They're usually slot machines. Which slot machine do I play? And I want to learn by playing, okay? And why it's a slot machine is relevant here is I have to put some money into play, okay? And the performance metric that's appropriate in this context is regret. In other words, one of the machines might be much better than the other machines. If I played that the whole time, that would be the optimal action. Just play the one machine or apply the one defense in a certain cyber engagement. But a priori, I don't know what that is. And so the regret is, what's the difference aggregated over learning? The difference between what I actually do, and that includes trying some suboptimal actions. What is my regret or cumulative regret? So just to, there's a lot of excitement about computational game theory and how AlphaGo and AlphaZero and things like that. And they're learning to play a game, but the key here is that it's against a stationary non-adaptive opponent. And we can do simulation to put the game into a state and then see what a certain play, certain action results, okay? And so this is an offline technique. I can, and Google spends months and big server farms of CPU time to learn these strategies, okay? So there is a cost, namely how much computer time and so on. And just a depiction here is the adaptive player, this is key, plays against a fixed dumb opponent until, using some Q-learning or reinforcement learning technique, becomes reliably superior to the dumb fixed opponent. And then the roles are switched. You make that superior player, you fix the strategy for playing, and then you have a new adaptive player that starts playing against the now fixed opponent, not so dumb anymore, until that adaptive player is superior. Okay, so this is a concept of self-play. And in a real adaptive adversarial engagement, a key assumption that complicates things a lot if it doesn't hold is that the adversary is not adapting or learning as well. So the adversary is fixed. If you have both sides adapting, you can get into chaotic dynamics and some crazy stuff. The other twist is that, as in the multi-hour bandit, you're paying while you play. So if you're doing suboptimal actions, there's actually some real world performance that is lost. So at a slot machine, I'm putting money in, I'm trying to learn which machine to play. In a cyber engagement, if I do suboptimal things, I may get compromised or even incapacitated as a cyber asset. Okay, so I mentioned regret before. So regret is the difference between a current performance that I'm obtaining by taking the action that I have and some omniscient oracle-like optimal performance, what I could achieve if I knew what the best strategy was. And cumulative regret, and really I'm going to be talking about cumulative regret, is the accumulated regret while learning. So it's the total number of quarters I put in to play the slot machines as well as what I got returned. So this measures the cost of suboptimal performance while you're learning. And you're using performance in that domain as a measure, not convergence, the rate of convergence in some abstract L2 norm or something. So again, I apologize. We've all seen reinforcement learning many times. But the key here is in the blue box that there's no prescription in general for how to select a state and an action to learn most effectively and quickly. So that's what I'm going to talk about a little. If I select an action that's myopic, the best current option available, I won't be doing any exploration and I could get typically locked into a local minimum. If I use this myopic, greedy approach. On the other hand, if I have unprincipled randomization, I'll fail to exploit what I've learned, and that's going to be suboptimal with respect to regret. Okay, and so a technique that is currently widely used and a champion in this domain is something called upper confidence bound paradigm, and I'll walk you through that. So intuitively, if I perform action I a number of times, I'll have an empirical estimate. I'm calling that M sub I for what the reward is. So it's the mean reward for trying action I, and this is in some state. Okay, and action I has been tried some number N sub I of times, and just using basic statistics and probability theory, the uncertainty in MI is proportional to 1 over the square root of n. Okay, the number of times I've tried. And that sort of falls out of Chebyshev's inequality. And it's true regardless of what kind of distribution the rewards have. Okay, so the current mean estimate plus some multiplier of 1 over square root of ni. So that's roughly the standard deviation of the sample mean. Estimates how large a reward action could be probabilistically. Okay, again, we're using Chebyshev's inequality. And so this uncertainty is going to decrease with more tries. And if we have multiple agents in a cyber defense system, multiple servers, multiple assets that are doing this learning, we can sample these things. We can make NI grow larger over time, okay, by using multiple agents to implement these sampling techniques. So with that in mind, that this upper confidence bound derivation is basically the sample mean plus some estimate of the standard deviation is an upper bound with some probability on what the reward could be. Here's a situation where I try action 3 and I get this random reward. Okay, so that's the setup. If I do that multiple times, I'm going to get what are depicted here as empirical means for these different actions, A1 through AN. And the green bar is the confidence interval, namely a multiple of the standard deviation of the empirical mean. And it depends on how many times I've sampled things, right? So I have this these red sample means and these green estimates, approximations of the standard deviation, some multiple of the standard deviation. And then the blue bar is the upper confidence band. It says this is with some essentially the same probability given the data I've got. Those blue dots represent the best that every action could be. Okay, and so to walk through this picture a little more detail, the best response, if I just looked at the means, I would pick A3 because that's got the best mean so far. So that's a myopic exploitation of the best response. On the other hand, if I look at A1, this could be better because the confidence bound for that sample mean is much bigger. And with the same essential probability as A3, I could have a higher outcome, okay? A better outcome for trying action 1. So what I want to do is figure out a way to randomly select according to the probability. So I might want to select things that have the largest upper confidence bound, the blue bars, in a way that's proportional to what those where those blue bars are relative to each other. Something that's low, I don't want to give up on it, but I have to sample it more. Okay, and I can do this with multiple agents. So I can make this in a distributed way and sort of share the information among agents episodically. So with respect to how the sampling is done, I'm going to let UI be the UCB value action for action I. And I'm going to exponentiate that with a multiplier T. So I'm going to define V to be that exponent, and then I'm going to normalize the V's. So the V's are all positive, and when I normalize them, I get a probability distribution. And observe that when T is 0, I get a uniform distribution. So I'm sampling everything in an unprincipled uniform way. I'm not learning anything as I'm doing sampling that way. But as T gets higher, I'm going to put more weight on higher values of U. And as T goes to infinity, I'm only going to sample in the limit the highest reward. Okay, so the takeaway here is that we can adapt from pure exploitation to pure exploration when T equals 0 to pure exploitation as T goes to infinity. And so we're going to have multiple agents do this. They're going to use UCB sampling the way I described with some values of T. And the key here is that at some rate, because I'm sampling suboptimal things, some of the assets that I have are going to be attrited. I'm going to have fewer samples drawn over time. So initially I'm learning a lot, but in my learning, I'm actually, because I have multiple agents, but as I'm losing agents because I'm making suboptimal choices, the learning rate goes down. To compound the problem, compromised agents, I can't assume they've been compromised and they're still truth tellers. They're performing the algorithm and performing the mission honestly. So at some point I have to deal with a Byzantine generals problem in this scenario, which leads to some blockchain things that I'm not going to talk about in this particular presentation. So what we're going to do is use a time-varying epidemiological model to understand the dynamics of how these trade-offs occur, okay? I have a lot of learners, my learning rate is high, but as time goes on, I'm going to lose some, even though my performance overall is better, but I'm still attriting, okay? And I'm going to include some Byzantine agreement thresholds and mission requirements in this as well. So the epidemiological model is based on this compartmented model of some agents are susceptible or operating normally, denoted by S. Some agents are compromised, overrun, denoted by C. So these are a real epidemic. These are infected. And some agents fail, die, cannot be restored. So they're out of the system altogether. So some compromised agents, I'm assuming, can be rebooted and restored. But once something is dead, can't be restored, it's out of the system. So the state equations describing this time-varying dynamical system are given here. And the key thing here is that these parameters, alpha 1, 2, and 3, describe transitions between different states and different assumptions about the learning rate and the attrition rate and things like that. And it's time varying because as time goes on, the number of agents that I can rely on is decreasing as well, okay? So I have a 1 over square root of NT in there to denote that. That's roughly that standard deviation and regret that arises in these UCB algorithms. Okay, so to explain the setup, I've got these 3 plots, this sort of standard 3 compartments in this epidemiological model of susceptible systems, compromised systems, and then monotonically increasing inoperable systems, systems that are just going to disappear. Now, what I'm going to add to that is Byzantine threshold. So as I mentioned, once systems start being depleted or compromised, I need to maintain at least 2/3 that are going to be reliable in order to survive this sort of Byzantine failure scenario. And so that Byzantine threshold is depicted by the purple line going through there. Now, when the blue line, which is the number of susceptible, let's say known good, known performing, crosses this Byzantine threshold, I'm calling that the critical Byzantine value. It's that red vertical line that says I can no longer trust the system because the number of trusted components is less than 2/3. Okay, and so basically the blue line, what I'm looking for, this purple line, is the line that shows 2/3 of what the sum of the red line, the compromised, and the susceptible are together, ignoring the inoperable ones. So ones that are offline, I don't communicate with, they're gone. Okay. And finally, I'm putting in a green line here that says I need at least so many assets or resources or servers to operate correctly to sustain the mission. So whatever the mission computation is, I need that many. So here I made it 50 just to have a reference point. So what you can see is in these simulations, according to how quickly, what the attrition rate is, how which depends on how suboptimal some of the choices are, I can get a situation where I have slow learning and high attrition. As a result of that, results in a loss of functionality early, which we can quantify as shown here. under certain other assumptions about how the system, the rate at which it learns, and how robust the systems are to suboptimal choices, I get a different performance curve, and I push that red line out further, and I can sustain mission performance much longer, okay? And here's another setting of parameters that's even better. I push that red line out to the right, and I stay, at least in this time frame, I stay above the green line. So what we have is a way to model UCB type learning in a reinforcement adaptive cyber defense system. And then we have a way in which we can use time varying epidemiological models to say how is that going to perform in the model, using the model assumptions. So to summarize, we've developed principal ways to model these attritable online learning systems. In work that I haven't talked about in this here, but one can wrap this up in a blockchain type algorithm for the Byzantine general problem. And we've talked about these dynamics. We can use this in cyber defense, resiliency, and survivability, where we want to get decision advantage in cyber operations. We can adapt faster than the adversary in an engagement. And we do that by operating inside an adversary's decision loop. So finally, people who are interested in talking about this, want to collaborate in any way, moving it forward, get in touch with Roger or me, and send it if you have trouble getting access to the papers I mentioned initially, or want to see some other work we've done. Let us know. Thank you.